Anyway, so let's wrap up the little stuff we have from paging and memory management from before, and try to catch up on the storage component, right? I haven't get your homework, your exams yet. I'll try to give it on Friday with the projects and stuff, right? So the part we were discussing before we left was on thrashing, right? So essentially the idea of thrashing is if you don't have enough pages, if you assign fewer and fewer pages to a process, there reaches a point where you spend most of your time trying to move pages in and out. Remember, the whole memory management idea here is you have far fewer fast resources than slow resources, and you're trying to play a game by moving stuff back and forth. And at some point, it gets to be so bad that you can't bring enough stuff in. You basically bring stuff in, and then you have to throw stuff out. And that's called thrashing. Your system basically doesn't do anything, right? Which is not what is happening with the Windows side. I think it's deadlocking on something. It's waiting for some whatever, right? But when it thrashes, your disk is busy, your machine is trying to do something, your CPU utilization goes down because your CPU is not doing any work. All you're doing is essentially trying to bring the pages back and forth. So you bring a page, you don't use it enough, and then you throw it, right? And in a few slides, we'll see what's the idea behind why the problem happens. But you might have noticed it. Typically, if you have a machine with fewer memory resources, right? At this point, if you had a PC which had like 64 meg or something, right? Essentially, you'll be sitting there most of the time trying to get the disk going, because you can hear the disk going wild, right? Even if you have 256 meg of memory, you'll notice that if you go from one process to another process, there's a whole bunch of disk activity while it's trying to bring in and stuff, right? And that's the notion of thrashing. And you know it when you see it, because when this happens, your disk is going wild and nothing is really happening for you, right? So essentially it's busy swapping process in and out. And so it looks like if I move away, then it focuses on nothing, right? So if you look at the CPU utilization as some sort of metric, where you try to figure out how much CPU is being used, and as you increase the number of processes, you reach a point where CPU utilization goes to 0, because basically CPU is not doing anything. You're basically bringing the pages back and forth. Okay. So the reason why we run into thrashing essentially boils down to why demand paging works, right? The demand paging idea is you're bringing something from a slower memory, doing something, and then you're throwing away. And the reason why it works is because of the notion of locality, right? The idea here is you assume that processes typically go through something like the example you give here, where you do certain things over and over again, then you move on to another phase, right? So for example, if you're looking at a text editor, you are, say, entering text for a while, then you're formatting or something. So you go through different phases, and the idea is you have to have some areas where you go back over and over again, right? So if you had a program which took a straight line and went through the whole process, so if you had a program which started at main, and it had a series of lines, right? None of them ever repeated, right? Which means that every time you touch a new page, you'll have to do a page fall. You bring in something, you use it that once, and then you move on, right? You may reuse it depending on the page size. You may reuse it for a little bit, right? You may use the same addresses or same address for a little bit, but you don't get the same benefit as if you're doing in a loop. Because if you're going in a loop, essentially if I keep this in memory, then it's all set. Your program basically, your OS never gets involved. It's all the pages are brought into memory, and you keep going, right? So that's the notion, that's the locality that you really look for. If you have this locality, the more you go through in a loop, the more everything is set, OS does not get involved, all the pages are in, all your TLBs are good, everything is good, everything works fine. So in this case, if you're going through a loop, you pay the cost once upfront, and depending on the number of times you go through, you reap benefits, right? This is for program text. And the same happens for data, right? If you have a matrix, if you have an array of integers, and the more you go through the stuff, if I can bring everything inside, then I benefit, right? So the idea is you have this locality. You go from locality to locality, but you have some locality. If your program does not have locality, then this does not really work. If your program used all integer variables, no arrays, and it just did a straight line code, then it's not going to benefit from any of this stuff. And once you have the notion of locality, thrashing happens when the locality that you're going through requires more memory than what you have, right? So let's say you're going through in a loop here, and if your text requires 1 megabyte, right? And if you only gave it 512 kilobyte, then you'll have thrashing because your program is going through this stuff over and over again, but it can't really use what it has. So essentially, every time it goes through, it's going to run all over itself, and you're going to have trouble, right? So you want to figure out what the locality is, and you want to at least give it as much as the locality would require, right? And that's the notion of when thrashing happens and when thrashing. So if you can figure out what the locality is, right? So you need the notion of locality for demand paging to work, for most of the stuff we are talking about to work. And most of the programs have those. I mean, very rarely do you write a program where you start from main and then keep going in a straight line, right? And you only access integers, right? You probably do that for your programming 101 kind of class, but not any real programs. Real programs go through loops. They do stuff over and over again. They use arrays and stuff. So for the most part, it works. So the point that we can control is if you make sure that what the working set is, and if you can assign all the resources for the working set to be satisfied, then you expect that when you come in first to an array or a working set stuff, you bring in, so you first get the page faults to bring in all the code, you first get the page faults to bring in all the data. But once that is done, OS is not involved, and the program can make progress. And depending on how many times it loops, depending on how many times it stays in the same working set, you reap the benefits, right? So is that clear? So the way so that's the notion of working set, and we kind of look at it and say, yeah, there's a loop here. In the example that we had, this for loop is probably where the working set should happen or something, right? But when you're within the operating system, you don't have the hindsight. You don't know what the program is. All you see is references, sort of like what you're seeing for your homework project. You're seeing a whole bunch of references, and so you're trying to figure out if the OS can figure out based on the traces, based on the past, what you're doing, whether you're getting into a point where you're accessing something over and over again, and then it can try to give you more pages or less pages, right? So think of how your homework project the pin traces look like. How many of you actually finished the homework project? It's due on Friday, right? So did you get a chance to look at the traces? Did you get a chance to see what references are going through, right? So that's an excellent program to see. Write a small matrix program, and you can see your program, the instructions going through the same addresses. That's the first column, right? And you can look at the data addresses to see they are being accessed in the same stuff, right? So basically, you have some trace like that. So OS can keep track of those traces, and using that, you want to figure out whether there's a working set happening and what the working set size is. Because if you know what the working set size is, then you should assign at least that much resource to the process. Because if you assign less, then you'll have thrashing, right? So for this to happen, you have to know how far back you have to look at, right? So you have the traces sort of like your pin trace, right? You cannot look. So you don't know how the program is running. All you know is these traces. You say 1, 2, 3, 4, 5, 1, 2, 3, 4, right? For example, let's say these are the traces, right? So you want to figure out, by looking at this, it looks like working set might be of size 5, right? So if you look at this, it looks like 1, 2, 3, 4, 5 is repeating, and so on, right? So this is what you want to find out. To find out this from within the operating system, right? Remember, OS only knows what has happened, not what the future is, right? So let's assume that this is what has happened so far, right? It has to keep track of something in the past. It has to know how much to look for, right? So let's assume that you decided to look at 3 things in the past, right? So at this point, you don't know, you don't have enough information. You go here, and you can assume that 1, 2, and 3 are part of the working set. You go here, right? Now it's changed, right? So you don't know whether this is part of the working set. Then you go here, right? What does it tell you about how big the number should be? I chose 3 here, right? 3 is the number of traces that I'm looking in the past to try to figure out if things are repeating. So if I look at the 3, right, then when I go here, now it becomes 1, 2, 3, 4. I mean, it now becomes 2, 3, 4. So I don't see any repeat, right? So you need this number to be larger, to be at least as big as the working set, because if it's smaller, you won't see it. It has to be bigger than that. So if you had it like, say, like 6 or something, then when you get here, you can say, I'm saying 1, I saw 1 in the past, right? So maybe those are part of a working set. So the larger window I look at, the more I can tell what working set might be. Yeah.
Is that kind of just like generally the more of the program you can afford to load in, the better performance you get, because then you're just not page faulting as much, or is that?
So there are 2 components. One is, if you give more memory to you, most likely you will be happy, right? But in a machine, there are other processes, right? So you're not trying to see how much. Granted, if I give you more memory, you'll be happy. But I want to make sure I give you no more than what is necessary for you to be happy, so somebody else can be happy, right? So that's a good observation. So if I started this with like infinity, right, then that shows that the whole program has a locality, right? Because you're still trying to find. So you wait till you get infinity, and then you look at the whole stuff. So in that case, you would keep your whole process in your memory. In which case, you'll be happy. Everybody else will be unhappy, right? So that's the second case. So if it's too large, then you may find. So, let's look at a case here. 1, 2, 3, 1, 2, 3, right, and so on. And then let's say 4, 5, 6, 5, 6, 5, 6, and so on, right? So what happened is there's a working set here, and then this 4 is just left over, and then it's repeating something here, sort of like the for loop here, right? So you go through this stuff for a while, and then you switch over to the next one, and then you go through the other stuff for a while. If you had the window that you're looking for to be really large, that it encompasses the whole thing, right, then you may allocate that much, right? So you really want to only see, there are 2 working sets, so you don't have to give as much for 2 working sets, because the program is going for this for a while, then it kind of stops, and then it goes to another one, right? So you want to be able to look at so the choice is pretty important. If it's too small, you don't see the big picture. If it's too large, you see too big a picture, and you see multiple working set, right? And you have to allocate more than whatever you see. So if you allocate less, then you'll see thrashing, right? Because you're going through this loop over and over again. And so that's the idea behind, if you want to avoid thrashing, how do you do that, right? And again, if there's only one process, you don't have to worry about this stuff, and if there are more, then you worry, right? So I hope you kind of see the connection. We don't explicitly say it yet about how the memory relates to the processes, right? I'm waiting for finishing the files, and we can look at all the stuff together, right? But the idea here is, if it had only one process, many of these problems go away, right? But now think there's other processes. So the OS is trying to figure out how much should I give to each process, right? And now think of what happens when you have context switches. Now think of what happens when you have threads. Think of what happens when those things are independently happening when they're allocating stuff, right? So you create a new process that wants more memory. So you have to take a memory from somebody to give it to that one, right? But if you take from a process which is already running, which has less than its working set, then that will start to thrash, right? So if you do a fair allocation and say, I have 10 pages, and I gave 5 to one process and 5 to another process, a new process comes in. So if I decide to give all of them 3, right, it may look, so initially I had 10 pages. It was given as 5 and 5, right? And now another process came in. So let's say I decide to give it as 3, 3, and 4, right? which may look good from a fairness perspective because now I'm being fair to everybody, right? But if you did that, then this will kill you. So for example, if this process required 5, giving it 4 would mean that it's always thrashing, which means that it's not making any progress. It's not getting any CPU. Your disk is always busy. Your disk is bringing stuff. So this process is not making any progress at all, right? And the disk is busy, which means that these two suffer because if they want to go to the disk to do a swapping, they suffer. This has 4 pages, which it's not using anyway, right? It's bringing the whole stuff, right? So in that scenario, it might be better to just not give any resources to this at all. You may take the 4 and give this to 5 and 5, right? So the fairness argument would say I should give everybody enough. But the reality may be I may give you fairly some resource, which means that you don't make any progress at all. You're basically thrashing. You're basically trying to bring the pages in kind of stuff. So these notions are important precisely because you have other processes, right? And that's what makes the OSS complicated. If you look at each component, if you look at the process scheduling or page management and all those things, they all are fairly straightforward. But the interactions of how these things affect each other is the reason why Microsoft takes 6 years to build the next operating system, right? Even though for a company which has built this operating system for a long time, getting that parameter right for a typical user is hard, right? And we haven't added another component, which is the file system component, which adds its own set of caches and stuff, and we'll try to put them all together and how you might how they interact with each other later on, right? Unfortunately, Linux thing does not work with the remote. So here is sort of what you have to do. You kind of look in the back, right? You figure out how much you want to look at the window size, and you try to see if there are repetition in the past. And so you have to keep. So the longer you have to look back, you have to keep track. The OS has to keep track of all the pages that were accessed, right? And build its table, right? And that could be tedious because you have to keep track of all these things, and that's usually not what you want to do, because every time you have to set the page to be protected, and when a person reads or writes it, you get a page fault. You can keep track of what was accessed and build these things in memory and stuff. And again, the longer you keep, the longer the trace you keep, that needs memory, right? So memory has to come from somewhere. So the memory comes from some other process. So instead of giving to a process, you can use the memory to keep track of these stuff, right? So you don't want to do that. So what you do is you use hardware support, right? And one of the hardware support, so you can do that with the reference bit, right? So the idea here is so let's assume the process is going through something like this, and I want to figure out, it's going through 1 to 3, 1 to 3, 4, what have you, and I want to figure out what the working set size is, right? And I don't want to do it precisely. So the way we do that is using reference bit, where you say, assume that all these pages have a reference bit built in, hardware supported, and you set them all to 0, right? For every page to be 0, right? And let the process run. Come back after some time, right? You don't want to come back after every tick. You come back after 10,000, some number, right? Come back and see which pages were touched, right? And how many times, right? If you don't keep the count, it'll tell you. So in this case, suppose our window size was this big, right? Let's say this big. So we set all the reference bit to be 0, and at this point we come back to see what happened, right? If you had a bit field, all the bits would be set of all the pages. 1, 2, 3, 4, 5, and 6 would be set, right? Which means that all of them are accessed, but it does not tell you how many times some things were accessed, right? Because the working set depends on you knowing what the count is. So you can't use a bit. You need to have a counter, right? And the simplest counter you can have is 2 bits, right? In which case it can count up to 4 values. So if you look at this case, you can say this was accessed 4 times, this was accessed 4 times, this was accessed 4 times, this was accessed 1 time, this was accessed 1 time, this was accessed 1 time, right? So you can look at the reference bits at this point and say this was accessed 4 times, 4 times, 4 times. You can draw your conclusions, right? So this depends on the time that you have to come back to and how big a size you have, right? Yeah.
So because those they have higher counter values, does that mean that they're more likely to be loaded or kept in memory?
I'm sorry.
Because like 1, 2, and 3, they've got a higher counter value.
Yeah.
4, 5, 6. Does that mean that they're more likely to stay in memory, or rather that they should be more likely to stay in memory?
So it's likely that they are in your working set, right?
Okay. Yeah. Yeah. So you want to keep them in then?
Yeah, you want to keep them. You want to keep them, or so you can draw conclusions on how big them. So if for some reason you have to reduce the number of pages for this program to 2, you can say you can't do that because the working set is 3. So at least have to give it 3, right? And as you can see, it doesn't quite work when there's a transition, right?
Transition seems like it.
Yeah. So that's why you have to have this. So it's pretty much magic. You're trying to figure out what this number is. It does not work in transition because at transition, you'll keep these pages on for a while, right? Because it still thinks the working set involves. If you look at this case, right, the working set is no longer 1, 2, and 3, but if you measure it, you'll think that it's 1, 2, and 3. So you'll keep. So you're not keeping 1 to 3. You're at least giving it 3 pages.
Okay.
Right. You may keep the 1 to 3, but that's a separate process, right? But here you're deciding that you'll at least keep 3, and eventually you'll go into this 5, 6, 5, 6 mode. Then you see you only need 2, so I could potentially take a page away from it, right? I mean, I could give it 3, which won't hurt it, but I can't give it 1, in which case it'll hurt it, right? And the larger the page size I have, the better I can do, right? So that depends on the hardware, right? We can't solve this with 1 bit. We at least need more than 1 bit. But if you give me like 10 or something, then it's good. And if you can make this thing smaller, then we won't run into this problem as much, right? So why would you keep the amount of time that you come back to larger or smaller? What's the rationale behind having it longer or shorter? So this is the interval where the OS comes in, sets all the bits to be 0, and lets the process comes in, go ahead, and then when it comes back and reads the reference bits, does what it has to do and let it go, right? And in the first case, the interval was 10,000, and they say improvement would be 1,000, right? In the second case, they say improvement would be if you had a bit size of 10 bits and 1,000 or something, right? So why would you want to have this number smaller? Yeah.
With a smaller number, you can probably predict performance more accurately, but it's also going to create more overhead.
Yeah. So if you have a smaller number, then essentially OS gets operating system gets involved. It sets all these page bits to be 0. It reads all the values, sets the page bits to be 0. It decides something, right? So you have to find a balance, and depending on what the OS is, you have to find some, whatever the balance is, right? So would you do this for your desktop operating system, like a Windows sitting on a desktop? Would you do these? Or do you think Microsoft OS does that? I don't know, but I'm asking. Have you ever run into a thrashing situation where you move your mouse and then the whole PC just goes wild, your disk goes wild, you can't do anything, but your disk is just going wild, right? Sometimes it goes wild and then everything is fine, right? When you have enough memory, it'll go wild and then it'll be fine. Sometimes it'll keep going wild, right? How many of you run a machine with very little memory, like 64 meg or 32 meg or something? No one? What's the minimum requirement for Windows XP? I think it's like very small, right? 8 or 16 or something. The absolute minimum that Microsoft requires you to boot Windows XP, it's very small, right? think, if I'm not mistaken, it's like 8 mega something, right? It's not very large for whatever the advertising purposes. They don't say we at least need 2 gigs of memory for you to have useful behavior, right? And if you look at the low-end PCs that you buy, like $200 PC or something that people buy for people who don't understand all this stuff, buy for their home, right? My grandma or something, right? They buy this PC which has like 128 meg or something. And they say, oh, my machine is very slow, I need to buy a new machine, right? And they have like probably 3 gigahertz processor sitting there. And you must have seen those, right? Like they have like 3 gigahertz processor and they say, oh, my machine is slow, I need to upgrade, right? And sure enough, the machine is very slow because nothing is happening, because whenever you touch the machine, it feels like it's up and running. I mean, the disk goes wild and stuff, right? And this is what is probably happening. And in those situations, since the memory is so low, you don't even have to do anything within the operating system. You can just buy more memory, put it in, machine runs fine, right? Yeah, hopefully none of us are doing this, and it appears like none of us are doing that, right? Which also brings up an issue of, remember, if you had no other processors, then you can give all the memory to one process. But if you have other processors, the OS would like to have a notion of acceptable page fault frequency, right? So if life is too good for a process, then you can probably take some pages away from it, because it's not getting any page fault at all. So if you draw sort of like a graph where if you assign more and more frames to a process, right, eventually at some point the page fault rate goes very low, right? So the OS can decide that if a page fault rate for a particular process is very low, then you can take away some frames, right? Because in the interest of balancing global behavior, right? So if it's too low behind the lower bound, then you can take some pages away from the process, knowing fully well that that would make it have, so if you take more frames away from this process, then essentially the line moves towards the y-axis, right? So which means that the page fault increases, and it may be deemed okay because you're willing to give each page a certain number of faults so you can service other processes, right? So the goal of the OS is not to reduce the page fault for a process, is to reduce the page fault for the entire system. So in that sense, you can have a notion where it says, you have too much memory, so I'm going to take some memory away from you and give it to others. So you have page faults, but as long as it's within certain bounds, I'm willing to tolerate it, right? If it goes beyond the upper bound, then we have trouble. But we don't want to have life too good, except if you have a lot of memory, right? What's the maximum memory? Yeah.
I was going to ask, so the OS then keeps track of the number of page faults for a program, and then interrupts every once in a while?
Yeah, it could, right? It could use that to, it knows what the number of page faults is, because every time page fault happens, it gets called, right? And all it has to do is keep in the PCB some counter which says the page fault happens,
okay,
right? Yeah.
So if it takes away frames from the process, but there's not a process to give them to, then
it won't do that.
Won't take them away.
No.
Okay.
Yeah. If you don't have any other process to take away, then yeah, he'll give you all the memory. But you hope that interesting machines have other processes, right?
And what if you don't have other frames to add once you're at it?
If all the processes are like they have to thrash?
Yeah.
Yeah, in that case, there's not a whole lot the OS can do, right? It can say, okay, you need 100 frames and this one needs 200 frames, but I only have 100, right? I mean, there's no magic, and it'll thrash, and it can give a warning to you saying, add more memory, but I mean, it's pretty smart. I mean, if it can do all the stuff, it's very smart to know that at this situation, there's nothing it can do. You need more memory. You have to buy more memory, and that's it, right? How many of you have like 4 gigs on a 32-bit machine, a desktop machine or something? And you can't actually have 4 gigabytes of memory, right? Because even though 32-bit machines can address 4 gigabytes, you can't really use 4 gigabytes because some of the I/O devices do memory mapped I/O and stuff, right? So they never assume that any human being would be able to buy 4 gigs of memory. So you lose some amount of memory, right? So unless your OS is designed for those stuff, you can't really, right? But 3 gig is sanely you can add, right? And I think most of the new Macs, you can add them for not a whole lot of money, right? Compared to a few years back, I think 3 gigs is not that expensive, right? For a desktop or laptop or whatever, right? So in that situation, it does not have to worry about these things because you have the maximum amount of memory that you can possibly have, right? And if you're still thrashing, then I mean, there's nothing the OS can do, right? Because you can't add more memory. That's the maximum amount of memory you can have, and you should be fine, right? Yeah.
Just a little off topic, but is that kind of the motivation for switching to 64-bit
Yes.
architecture?
Yes. Yeah. So when the switch to 64-bit, kind of happened for the workstation in like 93 or something, the rationale was you'll run out of memory, you should have this stuff. And back then we kind of laughed when back then machines had PCs had like 4 megs or something, right? 93 time frame, right? And when somebody said you may have 4 megs now, but you can't have more than 4 gig, right? That seems so far off, right? But now I think like the 3 gigs of memory on a laptop adds like $100 more than 2 gigs, which is the base memory on at least the Macs, right? So yeah, you do run into that problem. But we didn't think that we'll get into that thing. But yeah, that's one of the things. The other one is you can have larger integers, so you can do bigger calculations, right? You can do bigger calculations both in terms of integers, and also if you're doing vector, you can put all of them into one large integer, right? So if you're doing like an image processing or something, and so you only need bytes, right? So 32-bit is 4 bytes, right? So if you want to add 4 pixels and another 4 pixels, right? 4 image values. Let's say you want to add these to come up with one result, right? One way to do that is to put them into one integer. Of course, there'll be overflow and stuff, but you deal with those, and you can do those in parallel, right? So if you have 64, you can do a whole bunch more, right? Yeah.
So did you say that this page fault frequency scheme of the working set is actually used in our desktops, or are those more designed for bigger computers?
I don't think it's done in desktops. I don't have proof. I haven't looked at that code. But desktops, if you're thrashing, it's because you don't have enough memory, and all the system can come up and say, "Go buy more memory," right? There is no. It's sure you can boot. You can probably boot Windows XP for like 8 meg or something, right? But you can't do anything with it other than boot and look at it, right? If you run like your PowerPoint and all those things, I mean, you see like, it takes like 5 minutes to boot up that machine, right? The Windows machine, I mean, before it crashes. But, so in that situation, why bother to do all the stuff when all it has to say is go buy more memory, right? And that's one of the reasons why Apple can get away with a whole bunch of stuff, because they don't have to say go buy more memory. They can say our machines come with 2 gig, right? That's the base we sell. So the machines look snazzier when you buy it rather than Windows XP, where too many times I've seen the people have a machine which has so little memory that it's basically thrashing, and the people assume the reason is to upgrade to a new machine. And you're like, oh, it has 3 gig machine. Everything is fine. Just go buy like $20 worth of memory, and the machine will be fine, right? But the vendors, of course, will tell you to upgrade the machine. So if you take it to Best Buy, they say, oh yeah, this is 2 years old, and you should buy a faster machine, right? So the other stuff we can do with this paging and all those things is, if I figure out what some of these things, I can bring the page in before they are referenced, right? So if the OS starts to keep track of all these things, then it can get smarter, and you can say, I know that 1, 2, 3, 1, 2, 3 you're going through for a while, and you now into 4, 5, right? And suppose it started to go back again to 1, 2, 3, right? So you can remember that 1, 2, 3 was part of a working set of a while back. So when it saw 1 in the future, it can say, okay, I know you're going to ask 2, 1, 3, so I can pre-page it for you. I can preload it, so when you need it, it'll be there, right? If the prediction was accurate, you win. If the prediction was inaccurate, you lose twice over, right? Once you lose it, because you have to kick out some pages, you're bringing this new page in. It turns out you didn't actually need 1, 2, but you needed something else. So you bring in something, then you throw it out, and all those things, right? And we'll use a lot of this in the file system module, basically doing a pre-fetching. If I know what you're going to do, I can fetch something for you, so when you come here, it'll be faster. It depends on how good my prediction is. So there is a cost to doing this pre-paging. So if the ratio of the times that I'm right to the times that I'm wrong work in my favor, pre-paging would be useful, right? Pre-paging is useful a lot in file systems, right? Because you tend to access files in a certain order. So file systems always get few pages down the road from where you are, but you can also do that from memory, right? And you can do that because you are already learning all this stuff. The OS is learning what the trace is, how you're going through, right? The other notion is the page size, right? I mean, the page size defines all the stuff. So if you have larger page sizes, then you assume you get fewer page faults, but then you have a lot more fragmentation. So what page size you should go with, again, depends on what you're trying to do and how the machine is and all those things. And those affect like locality and all those things, right? If you have a large page, then a whole bunch of operations can happen within the same page. If you have a small number of page, you may be able to have locality, not have locality, depends on what the application is trying to do, right? And also the TLB reach. The TLB, remember the TLB register tells you, keeps a cache of all the pages that are being used. So TLB reach is the TLB size times the page size. It tells you how many memory addresses, logical addresses you can access while still getting the TLB hit, right? The larger the page size, that means all these logical addresses could still be held in the same TLB entry, right? The page size is small, then you potentially may not have so if the page size is small, that means your working set may involve more pages, which means that the same TLB won't work anymore, right? TLB is only worried about what is your working set in terms of pages. If you have a TLB set, let's say TLB of 3, in this case, right, TLB of 3 would be excellent because all these items could be in TLB cache for this here. And suppose you made the page size half as big, and it turns out that it became, let's say 1, 1, right? Let's say this is 2 of the, this particular page became 2, right? I'm going to say 1, 1 star, 2, 2 star, 3, 3 star, right? So nothing really changed, but now the TLB, if it had only 3 entries, it can only keep these 3, and then it has these 3, and so on. So you'll thrash on the TLB size, right? So you can thrash on the TLB or you can thrash on the main memory. Thrashing on TLB is not that bad because TLB is still faster than going to hard disk. So more typical workstations and above have variable size page sizes. They have dynamic page sizes. They can change the page size as they go along. Of course, you need the hardware support for doing all the stuff. And of course, it adds a lot of cost to the hardware. But those are stuff that you can do to get the best of both worlds. If the OS can figure out what the working set is, what the TLB reaches, then it can figure out what the optimal page size should be for that particular piece of code. And if the hardware allows it, it can change that, right? I know for a fact that DEC alphas use DEC alpha, compact alpha, or HP alpha. There used to be a company called Digital Equipment Corporation, which got bought over by a whole bunch of people. And they used to make a machine called DEC alphas, and they had dynamic pages, right? And those usually happen for higher end workstations and all those things where they can figure out what the optimal TLB size. You can't change the TLB size, but you can change the page size to compensate for the particular program. right? So that's. So let me finish this one. I think this we talked about when we started out at the beginning, right? Depending on how you access the matrix, row major or column major, and leave it as exercise to you. But essentially, if you go with the memory or if you go against the memory, in the first example, we change the column and row, and second, if you look at the for loops, right? One is for I equals, j equals, other is for j equals, I equals. Depending on what the program does, one can have much more page faults than the other one, right? Because the way you are accessing the program. And this is entirely up to the application which the OS has no control over. So if you were to write the code like that, it still works the same way, but your program would be terribly slow because you are working against, and there's not a whole lot OS can do because that's what you are accessing the program, right? And that's one of the reasons why you need to know all the stuff. And so essentially, that concludes the memory management component. We'll start with the files on Friday.